There is something in space that responds. And mind you, not in a poetic sense, but in a literal, physical, and measurable sense. In 1927, a Norwegian engineer named Jørgen Hals transmitted a radio signal into the sky. The signal is sent, it propagates at the speed of light, and then it returns, with a delay of 3 seconds. 3 seconds that, according to the laws of physics, shouldn't have existed. And this isn't an isolated incident. For almost a century, scientists, physicists, mathematicians, and astronomers have encountered the same phenomenon, a phenomenon that has been repeating continuously for almost a century, and that raises a disturbing question. What are these signals intercepting? The official answer is not convincing, and there are those who have found in the echo itself something much more unsettling, a message. This is the story of long delay echoes, the LDTs, and of what, perhaps, is watching us from the silence of space. But before we begin this fascinating journey, as we always do, we invite you to subscribe to the channel to support our work. To understand why long delay echoes are a problem, we need to start with a basic fact. Radio waves travel at the speed of light, 300,000 kilometers per second. It's the universe's top speed. There's nothing faster. When you transmit a radio signal and it bounces off something, the ionosphere, for example, it comes back in a time proportional to the distance traveled. An ionospheric echo, the standard bounce off the Earth's atmosphere, takes about 0.1 seconds. A lunar echo, the bounce off the surface of the moon, takes 2.7 seconds. These are the expected values, but LDEs do not match any of these values. The documented signals return with delays ranging from 3 to 30 seconds. In some cases, even longer. A delay of 15 seconds means that the signal has traveled about 4.5 million kilometers. A delay of 30 seconds means 9 million kilometers. To give you a reference, the moon is about 384,000 kilometers from Earth. So we're talking about distances that take the signal well beyond the moon, but still short of the nearest planets. In that region of space between the moon and Mars, there is no known natural structure capable of reflecting a radio signal with that power and precision. Yet the signal comes back, strong, clean, and clear, as if someone out there had simply held onto it for a few seconds and then sent it back. It's 1927. Radio engineering is still a young discipline. Experimental long-distance transmissions are an active and vital field of research. Jørgen Hals is a Norwegian amateur engineer. He is conducting long-range reception experiments when he starts to notice something strange. Some of the transmissions he receives seem to come back a second time, with an inexplicable delay. He reports it to physicist Carl Stormer, one of the most important scientific minds in Norway at the time, best known for his studies on the Northern Lights. Stormer is not the type to ignore an anomaly. He contacts the Dutch mathematician Balthasar van der Poel, and together they start a systematic observation program. What they report is published in 1928 in the journal Nature, perhaps the most prestigious scientific publication in the world, in an article that unequivocally describes the phenomenon. But it is one specific session that leaves the researchers speechless. On October 11, 1928, during a series of test transmissions, Stormer and van der Poel record a sequence of echoes with delays that change in a precise and orderly manner. 8 seconds, 11 seconds, 15 seconds, 8 seconds, 13 seconds, 3 seconds, 8 seconds, 8 seconds, 12 seconds, 15 seconds, 13 seconds, 8 seconds, 8 seconds. These can't be random numbers. They're not atmospheric interference. It's their own transmission coming back in sequence with precise and repeatable variations. As if it's following a pattern, the two researchers don't have an explanation. They say it openly in the article. And for decades, the phenomenon sits there unresolved, filed away among scientific anomalies. Before going any further, it's worth pausing over a detail that is often overlooked, but which is perhaps the most unsettling of all. The problem with long delay echoes is not just that the signal comes back late, but how it comes back. In 1934, the physicist Edward Appleton, who would go on to win the Nobel Prize in Physics in 1947 for his studies on the ionosphere, conducted a series of systematic experiments on LDEs, and he published the results in 4 consecutive articles in World Radio. The data he collected, presented as results, show something extraordinary. The delays are not distributed in a continuous and random way, as you would expect from a natural phenomenon. They cluster around precise and discrete values. A natural physical process, a bounce, an interference, a wave trapped in the plasma, produces delays that vary continuously. Appleton's data, on the other hand, show something different. The delays cluster around certain specific and recurring values, as if the signal were being held and released at fixed intervals. And this seems more like the behavior of a mechanism than that of a random natural phenomenon. Moreover, the long delay echoes return with an abnormal strength. In some documented cases, the power of the returning signal is equal to 1/3 of the original transmitted power. For a natural echo that has traveled millions of kilometers or bounced hundreds of times through the atmosphere, it's physically impossible. Every bounce, every kilometer traveled, takes energy away from the signal. Instead, these echoes return as if something along the way had amplified or retransmitted them. Science, of course, did not give up on the anomaly. Over the decades, several natural explanations have been put forward, so it's right to examine them before broadening the scope, but it's just as important to consider their limitations. The first hypothesis, the one that tries to explain these anomalies, refers to plasma. According to this theory, the signal would remain trapped in clouds of ionized gas present in the Earth's magnetosphere. This plasma could, in theory, hold the wave for a few seconds before releasing it. The big problem with this explanation is that plasma is inherently chaotic. A signal that remains trapped in plasma for 10, 15, 30 seconds undergoes massive distortions. It should come back degraded, fragmented, almost unrecognizable. Long delay echoes, on the other hand, come back extremely clean. The quality of the signal is comparable to that of a signal deliberately retransmitted by an antenna. Physical models of plasma estimate maximum delays of about 6 seconds under the most favorable conditions, and echoes that arrive after 15, 20, 30 seconds cannot be explained by current models. The second hypothesis is multiple reflection. The idea basically is that the signal literally makes hundreds of trips around the Earth before returning to the sender. But even in this case, physics doesn't cooperate, because every time a radio wave passes through the ionosphere, it loses energy. After 30 seconds of continuous bouncing, we're talking about roughly 200 trips around the Earth. The signal would be so weak that it would be indistinguishable from background noise. And yet, LDEs come back strong, sometimes strangely strong. For decades, it was argued that the equipment from the 1920s was too primitive to rule out instrumental artifacts. But LDEs did not disappear with technological progress. Amateur radio operators all over the world continue to report them. There are even online groups dedicated to documenting them. And when mainstream science can't settle a question, human thought inevitably begins to explore alternatives. In 1960, a Stanford astrophysicist named Ronald Bracewell proposed an idea that almost 60 years later has never been formally refuted. Bracewell is not a visionary on the fringes of science. He is a respected researcher, author of fundamental works in radio astronomy. And his proposal is, in its structure, surprisingly rational. The reasoning is this: if an extraterrestrial civilization wanted to contact other intelligences in the universe, it would face a fundamental problem. It doesn't know our language. It doesn't know our communication systems. It doesn't know how we would respond, nor how we would interpret a direct signal. The most efficient solution would be to send an automated probe, a physical device, near every star that could potentially host intelligent life, and leave it there waiting. The probe wouldn't do anything until it detected an artificial signal coming from the planet. At that point, it would receive it, record it, and retransmit it with a predetermined delay back to the source. To do all this, you don't need a common language. You don't need a decodable message. The simple fact of receiving your own signal, an echo signal, with a delay that's impossible for any natural phenomenon, would be enough to make it clear. Someone is here. Someone has heard you. Someone is responding. It's a universal technological ping, a "we're here," that doesn't require dictionaries. The Bracewell probe is, from a logical point of view, one of the most elegant first contact strategies ever conceived. And LDEs correspond exactly to what you would expect from such a probe. But the story doesn't end with Bracewell, because the mystery of the origin of this phenomenon becomes even more unsettling, and a real code to decipher appears. In 1973, a Scottish astronomer named Duncan Lunan returned to the 1928 data, analyzed them with methods that weren't available in the 1920s, and found something that radically changed the nature of the problem. Lunan takes the delay times of the echoes recorded by Sturmer and Vanderpool and uses them as coordinates. He places the sequential number of each echo on the y-axis and the delay in seconds of each echo on the x-axis. The result of this experiment is astonishing, because a star map appears. More precisely, a recognizable representation of the constellation Bootes, one of the brightest and most distinctive constellations in the northern sky. But there's an additional detail. The map doesn't show the constellation Bootes as it appears today. It shows it as it looked 13,000 years ago. As we know, stars move. Slowly, over the course of millennia, their positions change relative to the observer on Earth. What Lunan finds is therefore a map that takes this movement into account and indicates a precise position in time. In particular, the map seems to indicate the star system of Epsilon Boötis, a double star about 203 light-years from Earth. According to Lunan's interpretation, the message encoded in the sequence of echoes is unmistakable. I come from this star. I arrived in your solar system 13,000 years ago. A probe, or something, that would have entered Earth's orbit during what we consider to be human prehistory. And that waited, in silence, until we developed the technology for it to signal us. Throughout the 20th century, amateur radio operators and researchers worldwide documented anomalous echoes. In 1967, a group of researchers from Stanford University, led by Crawford, repeated the experiments with modern equipment. They confirmed the phenomenon. Delays of 2 and 8 seconds are the most frequent, but they were unable to reproduce the longer echoes from the 1930s. In the 1980s and 1990s, WGHF and UHF operators began to document echoes on much higher frequencies than the original ones, 432 MHz and 1,296 MHz. Classic ionospheric explanations don't hold up even in theory. In 2009, a Danish radio amateur, Oz4UN, published documentation of anomalous echoes on the 80-meter band. But the most significant breakthrough comes in December 2024, when a study titled Unraveling Mystique: Long Delay Echoes, authored by John and Gerald Tedesco, is published in the Open Journal of Applied Sciences. The study is different from everything that came before for a specific reason. It doesn't use amateur radio transceivers, it uses radar. The researchers used a 3-centimeter X-band marine radar and a portable millimeter wave Doppler radar system in an analysis that lasted 2 years. What they found were propagation anomalies, including long delay echoes and what they call unexpected field echoes, which do not correspond to any standard propagation protocol. Radar signals, by their nature, eliminate much of the ambiguity of amateur radio transmissions. They have defined power, defined direction, and precise reception protocols. When a radar sees a signal return with an impossible delay, it's no longer a case of a radio amateur misinterpreting interference. The study, after recording this data, explicitly points to a correlation with unidentified anomalous phenomena, the so-called UAPs, and openly calls for further research. Almost a century after Jürgen Halse's letter to Carl Stormer, the phenomenon is still there, increasingly documented, studied, but not explained. Long delay echoes remain to this day an anomalous phenomenon without a definitive explanation. As we have seen, official science has tried to attribute them to natural processes, plasma, multiple reflections, instrumental errors, but none of these explanations hold up to rigorous analysis. Ronald Bracewell provided a theoretical framework that fits the phenomenon perfectly, and it has been developed over decades of SETI research without ever being formally disproven. Duncan Lunan found in that data a structure, a map, an origin, a date, which is either the most extraordinary statistical coincidence in the history of science, or it is something else. At the moment, we have no certainties, but what we do know is that something, somewhere between the Earth and the boundary of the inner solar system, receives our signals and sends them back, with a delay that shouldn't exist, with a power it shouldn't have, and from a distance where there shouldn't be anything. Let us know in the comments what you think, or if you have looked deeper into this extraordinary and mysterious phenomenon. And if you want to support our work, don't forget to share the video and subscribe to the channel. Until the next story.